Hello, students. Today we're trying to prove a famous theorem which says if you add up the cubes of the first n numbers, that's the same as just adding up the numbers first, but then squaring the result. Okay, so how do we do it? Okay. Well, I think it would be easier if we rewrite this sum here. We can rewrite this guy inside as n times n plus 1 over 2 using a famous formula. I made a video about it. This guy is the same as this guy. So all we have to do is prove this. So we want to show that this is true. How do we do that? Well, let's proceed by induction. Our base case is if n is 1, we get 1 cubed on the left side, and then the right side becomes 1 times 1 plus 1 all over 2 squared. And let's see, well, this 1 cube, that comes out to 1, and this comes out to 2 over 2, which is 1 squared, which is equal to 1. So 1 equals 1. This is true. Okay, now in an inductive step. For our inductive step, we want to assume that this formula is true for some fixed n. And we want to show that's true for n plus 1 as well. How do we do it? Well, we can rewrite this part as this, because we're assuming they're the same. So we can copy and paste this, but we'll replace these first n terms with this expression right here. Oops. This expression right here. Okay, now we just simplify this. Let's see if both sides are indeed equal. If we square this fraction, we get n squared times n plus 1 squared all over 4. Plus, we can expand this using the binomial theorem. N cubed plus 3 n squared plus 3n plus 1. And now what about this fraction? Well, the numerator becomes n plus 1 squared times n plus 2 squared. The denominator is 4. Okay, let's simplify these even more. To get rid of fractions, why don't we try multiplying both sides by 4? So if we do that, we get n squared times n plus 1 squared plus 4n cubed plus 12n squared plus 12n plus 4. And then the right side just becomes the numerator. Squared n plus 2 squared. Okay, now let's expand this stuff out. N plus 1 squared is n squared plus 2n plus 1. The rest of this stays the same. Let's see, n plus 1 squared, that's the same as n squared plus 2n plus 1. And then this guy squared is n squared plus 4n plus 4. Distribute the n squared. So we get n to the 4th plus 2n cubed plus n squared plus all this stuff. And on the right hand side, what do we get? Gonna have to distribute. There's going to be 9 things in all. So n squared times n squared is n to the 4th. N squared times 4n is 4n cubed. N squared times 4 is 4n squared. 2n times n squared is 2n cubed. 2n times 4n is 8n squared. 2n times 4 is 8n. And then we do 1 times all of these things. So you get n squared plus 4n plus 4. Wow, that's a lot. So much so that I don't even have room for all of it. So let's combine like terms. N to the 4 plus how many cubes are there? So we get 6n cubed in all. n squareds, 13 n squareds. What about n's? Just this, 12n. Constant term is 4. Okay, what about the right-hand side? N to the 4th, that's the only term with n to the power of 4. How many n cubes do we have? We have 6 of them. How many n squares do we have? We have 13 of them. How many n's do we have? 12n. And what's the constant term? 4. So look, these are the same. So that means we proved that if it's true for n, then it's true for n plus 1 as well. And therefore, the theorem that we're trying to prove is true. And remember, this is the same as this. So by induction, we are done.